Welcome back to linear algebra. Let's jump into Anki. You've got this green shirt on and this really bright light on my eyes because it's the morning, so I'm looking really good, I know. Thank you. If a matrix is in reduced row echelon form, what must be true of the first non-zero number in a row that does not consist entirely of zeros? It's got to be a 1. All right, there we go. So I'm going to grade the problems I did yesterday, and then we'll go from there. All right, so we got both problems correct from yesterday. Interestingly, the way they showed that the big matrix was non-invertible was they actually got one of the rows to be 0. So that's, I guess, a way to prove that matrix is invertible if you can get a row to be 0. So, all right, that's that. Now I'm going to jump into the proof for this section, and then I'll be back to recall how it's going in a little bit. Well, guys, that was slightly unexpected. We actually ripped through the proof for 1.5. So we're trying to prove if A is an invertible matrix and B is a row equivalent to A, then B is also invertible. I thought at first this felt like it was part of the row equivalence theorem, but I'm not sure it actually is. Anyway, the way we proved it is if A is an invertible matrix, then we know there is a sequence of elementary row operations that can convert A into I, right? That we know that, and then we also know that there is a sequence of elementary row operations that can convert A into I. What the heck am I doing? Okay, we also know that if there's a sequence of elementary row operations that can convert A into I, then A is invertible. So we're basically saying if A is invertible if and only if there's a sequence of elementary row operations that can convert A into I. If B is a row equivalent to A, then there's a sequence of elementary row operations that can convert B into A. If we can convert B into A and A into I only using elementary row operations, then we can convert B into I using elementary row operations. If we convert B into I using elementary row operations, then B is invertible. I think that logic was actually pretty solid. Yeah. True or false? This one was about the row equivalence theorem. This was about row equivalence theorem. So it's basically saying if there's a square matrix that is singular, aka it's not invertible, then the linear system denoted A times X equals 0 has infinitely many solutions. And I had a feeling this is true based on the row equivalence theorem, but I checked by creating a matrix, a 2x2 matrix that is not invertible, and then multiplying that out and basically seeing that, yeah, it is true. So if a square matrix is non-invertible, then it has infinitely many solutions for the matrix equation or the linear system A times X equals 0. And therefore, I think if a matrix is invertible, then we know that only the, what do they call it? The simple solution, what do they call that? When all the variables are equal to 0 for homogeneous linear system. The, what is that called? Trivial solution, that's what it's called. And then we did one more problem before starting 1.6 from a random unit we already did. And we got another proof. I was like, dang it, dude, we were just about to be done and start 1.6, but ripped through this as well. If A is an MXN matrix and A times the product of B times A is defined, then then B is an NXM matrix. Actually pretty simple to show. I think I could have done it a little bit clearer, but I didn't want to spend too much time redoing this because I understand it. If A is an MXN matrix, right, it has m rows and n columns. I didn't really need to state that, but sometimes I state stuff like that just to get my brain started. If A times the product of B times A is defined, then B times A must be defined. If B times A is defined, and A is an MXN matrix, then B must have M rows, or not M rows, M's columns. It's got to have the same number of columns as the A has rows, and B times A is an X by N matrix. So X meaning unknown, or variable, I should say. If A times B times, or A times the product of B times A is defined, and A is an MXN matrix, then B must have N rows. If B must have M columns and N rows, then B is a NXM matrix. So here we go. And guess what? I started 1.6, which is about more invertible matrices and linear systems, more on linear systems and invertible matrices. And so far what I learned is that we can use a matrix inverse to find or to solve a linear system. So that's interesting. All right, that's it for today. Talk to you tomorrow. See you.